Hello, in this session we focus on integration and we are going to be looking at trigonometric substitutions. Actually, we are going to be looking at how to quickly decide that you are doing a trigonometric substitution and then how to know which trigonometric substitution will be suitable for your integral. In particular, if you have any integral in which there is the square root sign and there is either sum of two squares or difference of two squares, and all these, they are reciprocals to apply. So for instance, when I have 1 all over the square root of a squared plus x squared, I will still make use of a trigonometric substitution. At the backbone of these substitutions, we have Pythagorean identities. The first one is cos squared theta plus sine squared theta equals 1, and then its derivatives. But the first useful formula that I would have to use whenever I come across an integration that needs a trigonometric substitution is cos squared theta equals 1 minus sine squared theta. A derivative of this is 1 plus tan squared theta equals sec squared theta. If you divide through by cos squared theta, you get this other derivative. And this derivative provides two other useful forms that we'll be making use of when we are doing trigonometric substitutions. They are, so this is the first one that I will need to be making reference to once I come across any of the above integrals. The next one would be that sec squared theta equals 1 plus tan squared theta. So that is the second one. And then the third one is derived from the second one by making tan squared theta the subject. So tan squared theta equals sec squared theta minus 1. And that is the third useful formula that we need to make reference to each time we come across any of the integrals mentioned above. Now, I go straight away to demonstrate. If I have integral of the root of 1 plus x squared, the first thing to look at is that what is the sign between the two terms? I have plus, and actually 1 is also a square, so there is sum of two squares. Anytime there is sum of two squares, you are to use tan theta for the substitution. So take note, wherever there is a plus sign between the two squares, you would use tan theta, in which case my substitution will be that x, the square root of the variable term here, equals tan theta. And from there you do your substitution and integrate. However, if I have the general form a squared plus x squared dx, I have to be very careful when putting the substitution. It is still a plus sign, sum of two squares, and I am still going to use tan theta. But the variable constant but the constant term that is squared is not 1 again. So I have to choose my substitution carefully in such a way that when I'm simplifying the expression inside the radical sign, I would not have complications. And so in order to do a correct substitution, I will be saying x equals the square root of the constant term. That is not 1. So the square root of that would make the coefficient of tan theta. So the square root of a squared is a. So put a tan theta. That is the difference that you would have to make anytime you see sum of two squares. In the case where we have, for instance, take an example, 9 plus x squared dx to integrate, the substitution should be x equals the square root of 9, which is 3 tan theta. In particular, generally, if I have integral of the square root of a plus bx squared, let us put it generally, the x, the substitution would be that the square root of the variable term, the term that has the variable x squared, I find the square root of all that term to have what I have on the left hand side for my substitution. So the square root of bx squared will give me the root of bx equals, I go now to the constant term and I find the square root, so the square root of a tan theta. So that is the general format for doing substitutions in which the integral has square root of sum of two squares. Example, integral of the root of 7 plus 15x squared dx. My substitution should again be the square root of the term in the variable there, which is the root of 15x equals the root of the constant term, root 7 tan theta. Even when you complete the square, if I complete the square and at some point I have 1/4 plus, let's say, x plus 3 all squared dx. To do the integral, my substitution would again be the square root of the term in the variable x, which will simply give me x plus 3 should be equal to, again I take the square root of the constant term, which is half then tan theta. So long as there is a plus sign, even I've said even with reciprocals of this form, the substitution will still take the same form, so take note. Now in the case where we have difference of two squares in the radical, there are two situations: square root of a squared minus x squared and square root of x squared minus a squared. In this case we have two situations: the case where the difference of two squares is such that the variable term is negative, and the case where the variable term is positive. In the case where the variable term is negative, identity 1, you can see that there is some identity in the expression 1 minus sine squared theta and then a squared minus x squared. So the substitution x equals sine theta will be appropriate. Whereas for the third substitution, we have sec squared theta minus 1, and we can see that there is x squared minus a squared in the radical sign. So in that case, we are to use but sec theta for the substitution. Again, you would have to make sure that if the constant term is not 1, you put a coefficient of the trigonometric function in such a way that your substitution would tidy up when you are simplifying. And so in this one, so once I see that the variable term is negative, I'm using sine theta. When I see that it is positive, I'm using sec theta. So take note. In this one, I would say that x equals the root of the constant term again, which is a, and then sine theta. While this other one would take x equals the root of the constant term, that is a squared, and then sec theta. That simply gives a sec theta. And in a general form, I will have again a situation where I have square root of a just a plus, sorry, should be, this time it should be integral of the square root of a squared minus bx squared, while this other one would take the form the root of bx squared minus a. Good. So in this one, there is difference of two squares, and the term in x squared, or the term in the variable generally, is negative. Once it is negative, I am using sine theta. To tidy up the substitution, I have to find the square root of the variable term as my left hand side of the substitution. So I will write the square root of b and then the square root of x squared, which is simply x, equals the square root of the variable term, which is a, and then sine theta. While this other one would be the square root of the variable term again, which is root b x, equals the square root of the constant term. So here there was the square root of the constant. No, it was already squared there, but here I didn't square, so I have to put square root there. And then now, since the variable term in the difference of the two squares is positive, I'm using but sec theta. An example in this case, I would have integral of the square root of 9 minus 4x squared dx. And so my substitution will be the square root of 4x squared, which is 2x, equals the square root of the variable term, the square root of the constant term, that gives square root of 9, which is 3. And then, since the difference of two squares is such that the term in x squared is negative, I'm using sine theta. So this will be the substitution for this one. And in this other case, an example would be integral of the root of, let us say, 20x squared minus 16 dx. Again, the substitution will be the square root of the variable term, which is root 20, then x, equals the square root of the constant term, which becomes the coefficient of my trig function that I'm bringing in. Square root of 16 gives 4, and since the variable term is positive in the difference of two squares, I will be using sec theta for the substitution. Even when you complete the square in the case of quadratic expressions inside the square root, you could complete the square and have integral of 5 minus x plus 1 all squared at some point. And so your substitution again should be the square root of the variable term, which is x plus 1 equals the square root of the constant term, root 5, times the trig function that is appropriate for this. As I said, where there is difference of two squares and the term in the variable is negative, you are using sine theta. Suppose I complete the square at some point and I have square root of x plus 2 all squared minus 7 dx. Then the substitution would be the square root of the variable term, which is x plus 2 equals the square root of the constant term, which is root 7. And then, since the difference of two squares is such that the term in the variable is positive, I would use sec theta. So summarily, once you see an integral in which there is the square root of either sum or difference of two squares, be it as an expression or as a reciprocal of it, like this other term, any of these reciprocals in this form will still use a substitution that we are just from treating. Where there is sum of two squares, you are using tan theta for the substitution, and the tricks that I've already said, that the square root of the variable term should be equal to the square root of the constant term, then tan theta. Where you have but the square root of difference of two squares, there are two options. Either you are using sec theta for the substitution or sine theta. If the term in the variable is positive, then sec theta should be used. If the term in the variable is negative, then sine theta should be used. I hope this helps in your integral problems where you have to do substitution using trigonometric functions.